we physicists have held up 100 years. Starting around 1916 for this photo A, black hole may very well be one of the most captivating and baffling peculiarities in the universe. They are huge monsters with regards to gravity, yet at the same time, for all intents and purposes, imperceptible to us. A black hole weighing maybe 2 to 4 million times the mass of the sun. However, in view of the research that was put into them over the last 2 or 3 decades, we've gone from knowing literally nothing about them to getting to find out increasingly more very close and personal things have recently gotten more insane. Kaku recently reported that we finally got a glance at what's inside a black hole, and this new data carries light to the subtleties the universe of science could have missed from the start. Join us as we dig further into black holes and uncover what's inside. Space is huge and awful. What are black holes? Before we get into the details of what Michio found, we have to discuss the basic. Although most of us have some idea of what black holes are, there's still a few holes in the right information. You see, in 1916, Albert Einstein published his theory of general relativity, which predicted the presence of black holes. At that time, the concept of black holes was absolutely hypothetical. It required an additional 50 years for the scientific community to find proof that black holes really exist. This occurred in the 1960s when they were considering the Cygnus X1 heavenly body and saw a strangely radiant blue star that was producing X-rays. The star was certainly not a stable object, but was circumventing a giant dark something. Upon further examination, it was seen that the X-ray weren't just moving around on their own. They were being sucked into the dark thing they were circling, hence the name black hole. This discovery was huge because it provided evidence that black holes really exist, and they weren't just an invention of Albert Einstein's wild imagination. While that was incredible, it also meant that there was this stunning substance in space that we urgently needed to learn about. So scientists from one side of the planet to the other got to work. This black hole was named Cygnus X1, and it is located in the group of stars in Cygnus around 6,000 light years from Earth. It was no small discovery. It's multiple times more brilliant than the sun and unquestionably dense, which gives it a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. This is why it is known as a black hole. The concept of a black hole is both intriguing and frightening. It is a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole will be pulled into it, gone forever. However, that part of danger makes it even more important to learn everything there is to know about them. Was this it, or were we just starting? The answer turned out to be the latter. After the discovery of Cygnus X1, researchers began to look for other black holes. They found that there might be nearly 100 million black holes in the Milky Way alone, but because they're so incredibly difficult to detect, we still don't have an accurate number. By all accounts, there are several million black holes in the Milky Way in our very own galaxy, which makes them even more important to study. So let's break it down. The main concern with black hole is always going to be gravity. Their gravitation pull is so intense that anything that enters it packs down cosmically until it becomes a singularity. In simpler terms, black holes are like vast vacuum cleaners that suck everything in. One of the most startling parts about the research into black holes is the fact that if someone were to fall into one, they would reach a point where they become a singularity. This process would happen slowly, and the person would die before the final form of reality sets. And so, let's just say that nobody should step into one, but they're everywhere. So could we be in danger despite the fact that the nearest black hole to Earth is around 500 light Years away, it's still close enough to raise multiple concerns. In 2012, researchers were able to produce the first clear photo of a black hole. The M87 black hole. This black hole was captured over several nights, and with each photo the scientists gathered more and more proof about it. They had to line up the individual photos to fill in all the gaps. In doing so, they were able to determine that there are 3 layers to a black hole. Is not just one single expanding hole of nothingness, as many people believe. Things are much more complicated than that. To even get to the nothingness part of a black hole, you have to make it to the first 2 layers. The first layer is known as the event horizon, which, while on the first layer, is the point of no return. Once you pass the event horizon, pressing forward is your only real option, and you will be sucked into the black hole. But the 3 layers just get worse from there. The second layer is the photon sphere, where light orbits the black hole. Any light that enters this region will be caught and cannot escape due to the black hole's gravitational force. Finally, we come to the third layer, the singularity. This is where everything that enters the black hole is compacted down cosmically until it becomes a singularity. The singularity is a point in space-time where the laws of physics, as we know them, break down, and we can't predict what happens next. Now, what makes all of this even worse is the fact that each black hole you study will be entirely different from the last. Sure, they do tend to follow the same 3-layer concept, but the way they function could be vastly different at this point. If this were anything else, all we would need to do is hop back on those telescopes and simply study the basics in detail. But with black holes, you can't really do that. Researchers can study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe into a black hole is not possible, because anything that enters the event horizon is pulled toward the singularity, where it is compacted into an infinitesimally small point. So you can't exactly waste billions of dollars just to get an impression every time, because the second the probe gets close enough, it will simply be crushed into nothing. Because of that clear issue, researchers are left with no choice but to study these objects in a 2-dimensional way, even though they are 3-dimensional. Singularities, as a general rule, to make matters even more challenging, there are also the 2 issues of each black hole being unique and the laws of physics as we know them breaking down when we try to investigate the interior of black holes. Traditional methods of scientific inquiry don't really apply to the study of black holes. That doesn't mean researchers haven't been busy. There are lots of different theories and explanations for black holes, and with each one, things get more and more fascinating. One of the most compelling theories about the formation of black holes is that they are made from collapsed stars. At that point, when a star depletes its fuel, it can no longer generate enough energy to counteract the force of gravity that is constantly pulling inward, so the star begins to implode on itself, shrinking and becoming denser as it does. If the star is massive enough, this process can continue until it turns into a singularity. To understand the concept of black holes in depth, NASA researchers turned their attention to the center of the universe. M87 astronomers observed a really powerful whirlpool of very hot hydrogen gas that was rotating at a shocking pace of 1.2 million miles per hour. The sheer power of the rotating gas disk should have caused it to violently fly apart in all directions. However, it didn't. Researchers discovered that there must be a titanic mass concentrated at the center of the galaxy to prevent this from happening. This massive object weighed as much as 2 to 3 billion suns, and it had to be a black hole. But that's not the only theory regarding black holes in 1963 New Zealand mathematician Royer used Einstein's equations of gravity to provide the best description of a rotating black hole. He showed that a rotating black hole wouldn't collapse into a point as previously thought, but rather into a ring of fire or a thin. The disk would rotate so quickly that outward forces would prevent it from collapsing. This rotating disk of matter is known as the aerosphere, and it's the region surrounding the black hole where the laws of physics begin to break down. However, the most interesting feature of core solution was that it predicted the existence of an Einstein-Rosen bridge, also known as a wormhole. This is a theoretical tunnel through space-time that connects two separate regions of the universe, or even two parallel universes. The idea is that if one were to fall into a black hole, instead of being crushed to oblivion, they would be sucked down a tunnel through the ring of fire and shot out a white opening into a parallel universe. To understand how this works, we need to look at the concept of space-time. In Einstein's theory, the reality we experience isn't composed of independent entities, but is interconnected, forming a four-dimensional fabric known as space-time. Objects warp this fabric, creating a gravitational field that makes other objects move toward them. Now, imagine a sheet of paper representing space-time. If you place 2 points on the paper and draw a line between them, this is a representation of how objects move through space-time. But what if you could fold the paper in half and create a shortcut between the 2 points? This is the basic idea behind a wormhole. Wormholes are high hypothetical passages through space-time that would allow for faster than light travel. If one were to fall into a black hole, the idea is that they could pass through the wormhole and emerge in a completely different location in the universe. To tie this theory together with Mach is recent findings, the key lies in the fact that our understanding of space-time and gravity continues to evolve with the discovery of black holes and the study of their mysteries. We are beginning to explore the very fabric of the universe itself. While we may not yet be able to travel through wormholes or peer directly into the center of a black hole, we have come a long way in unlocking the secrets of these cosmic phenomena as scientists continue to investigate the nature of black holes and space-time. Who knows what astonishing discoveries lie ahead? The universe may be stranger and more wondrous than we could ever have imagined.